In this set of videos, we're going to be talking about filters. So as an introductory motivating example, let's take a look at an audio signal S of t, which has a waveform shaped over here. We were able to decompose S of t as 0.6 sine of 6000t plus some noise to cosine of 3000t minus pi over 4. The first half here is a desired signal, and when I say desired signal, I'm like talking into a mic, and this is the signal I want. So the question I want to ask now is, how do I filter out the noise? Or how do I make y of t the output? So let's say this is the output, the desired signal. And the answer is to use a filter, but more so to use the idea of frequency. And what I mean by that is take advantage of the fact that this first desired signal has frequency 6000 and the noise here has frequency 30,000. And the idea here now is that h of omega, or transfer functions, differ across frequencies. The actual ideas and implementation is a little bit more difficult than what I'm going to write down here, but I'm going to write down the general idea of how this is going to work. So right now we have S of t, the audio signal, as a sum of the desired signal d of t plus n of t. So I'm going to call this d of t, I'm going to call this n of t. Now if I take the phasor transform, I'm going to get s tilde is equal to d tilde plus n tilde. Now I'm going to define h of omega as our transfer function as y tilde over s tilde. Remember that y is our output audio signal, the one we want, and s is the input with the noise. So then, if I multiply both sides by h of omega, the transfer function is now going to pick out the frequencies. So because d, our original signal, has a frequency of 6000, this is going to be h of 6000 times d tilde plus h of 30,000 times n tilde. And remember that h of omega is equal to y tilde over s tilde, so this is going to be y tilde. Now, because we want our output here to be equal to the desired signal, we want y tilde, this is what we want y tilde to be equal to d tilde. And the way we're going to do this is we want h of 6000 to be close to 1 and h of 30,000 to be close to 0. Hopefully with this example you get an idea now of how transfer functions can shape different frequencies and how, with a given specific frequency, we can pick h of omega to have values that we want, so that now we have our output equal to our desired signal. Let's take a look at low-pass filters now. So a low-pass filter can be designed by putting a resistor first, then a capacitor, or an inductor first, then a resistor, and we measure the output between the resistor and the capacitor. For all of these problems, we're going to use the resistor-capacitor model instead of the inductor-resistor model. The math is more or less the same, but we'll just stick to one for now. So the first question asks for the transfer function and its magnitude. So the transfer function h of omega, this should be familiar by now, should be zc over zr plus zc, which will then be equal to 1 over 1 plus j omega rc. The magnitude of the transfer function will be equal to the magnitude of the numerator all over the magnitude of the denominator. And remember that the magnitude of a complex number will always be the square root of the real part squared plus the imaginary part squared. So this is the real part. Omega RC is the imaginary part. From here, moving on to the next part, for omega close to 0, or omega approaching 0, what is the magnitude of the transfer function? So if omega is close to 0, then omega RC is close to 0, meaning this will be 0, so the magnitude of the transfer function is 1 over 1. For omega going to infinity, what is the magnitude of h of omega? So if omega is going to infinity, it's very large, which means here omega RC is going to be very large. So the denominator is going to be very large, whereas the numerator is staying the same at 1, which means as omega goes to infinity, h of omega should be close to 0. Now that we've taken a look at a low-pass transfer function, I'm going to talk a little bit about the plot of the transfer function and its cutoff frequency. So from the previous part, we know that h of omega is equal to 1 over 1 plus j omega rc. And now let's just suppose that rc is equal to 1. In other words, the transfer function is 1 over 1 plus j omega. Then, for this semester, spring 20, you don't have to know how to plot the transfer function, but you will have to understand how to read it. So for omega close to 0, we said that it was near 1. And note the scale here is 10 to the 0, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. And for larger omega values, omega will be really, really small, close to 0. So if we try sketching out the plot now, it'll look like something like this. Now, when we're talking about the cutoff frequency of a filter, we're talking about the frequency omega such that the magnitude of h of omega is equal to the maximum magnitude over the square root of 2. So what this means is, given this filter plot here, we know the maximum value is 1. 10 to the 0 is 1. So then, for this low pass, we're looking for omega where the magnitude of h of omega is equal to 1 over the square root of 2. So the magnitude of that transfer function, the magnitude here, should be equal to 1 over the square root of 1 plus omega squared. And if we take a look, we see that omega is equal to 1. So omega c, this means the cutoff frequency, it's also referred to as the corner or pole frequency at times, is equal to 1. And for a generic RC, so for a generic RC low pass, we can then say that omega c is going to be equal to 1 over RC. Let's take a look at a high-pass filter. And a high-pass filter is designed with a capacitor, then a resistor, or alternatively, a resistor, then an inductor, in comparison to a low-pass filter, which is a resistor, then a capacitor. So the first thing we're going to look at is the transfer function and its magnitude. So the transfer function h of omega should be equal to zr over zr plus zc, and this will be j omega rc all over 1 plus j omega rc. The magnitude of this transfer function will then be the magnitude of j omega rc all over the magnitude of 1 plus j omega rc, and this will be equal to omega rc all over the square root of 1 plus omega rc squared. Now for omega close to 0, so omega on both sides are close to 0, what is h of omega, or what is the magnitude of h of omega? So h of omega will be equal to 0, which implies that the magnitude of h of omega will also be 0. Now for omega close to infinity, what is h of omega? So for omega very close to infinity, omega rc will be really large, which means 1 in comparison will be very small. So we can rewrite h of omega as omega rc all over the 1 we can approximate as 0 as omega rc squared. So we'll get omega rc over omega rc, and it'll be approximately 1. The cutoff frequency, we can do the same thing where we let the magnitude of h of omega, so we know the maximum is 1, so we want to find the frequency where it's equal to 1 over the square root of 2. So this means we want omega rc all over the square root of 1 plus omega RC squared equal to 1 over the square root of 2. And it follows that picking omega equal to 1 over RC lets us do this. Because if we pick omega equal to 1 over RC, we'll get 1 over the square root of 1 plus 1, which is equal to 1 over the square root of 2. Now, if we wanted to plot this, we know that at omega close to 0, it's equal to 0. We have a cutoff of 1 over square root of 2 at 1. Sorry, we're assuming RC is equal to 1. So if we assume RC is equal to 1, we have a cutoff at 1 over square root of 2. And then from there on, it becomes closer and closer to 1. So it's going to look something like this. Now we'll be taking a look at the bandpass filter. So a bandpass filter is designed with a resistor and a capacitor. So we're going to have a low pass first, take the output of the low pass, then feed it through a buffer. So we have the same output over here, Vx tilde, and then we're going to feed it through a high pass. So the first question we want to ask is, what is the transfer function and its magnitude? So we did this calculation before with phasors and transfer functions, but the way to do this is to take a look at the low pass transfer function and then multiply it with the high pass transfer function. And this is going to be equal to 1 over 1 plus j omega r1 c1 times j omega r2 c2 all over 1 plus j omega r2 c2. And if we expand this out, it's going to be equal to j omega r2 c2 all over, we can do some foiling and say that it's equal to 1 plus j omega r1 c1 plus r2 c2 plus j omega squared r1 c1 r2 c2. Now if we want the magnitude of this transfer function, if we want the magnitude of h of omega, then we take the magnitude of the numerator, that's going to be omega r2 c2, and then the magnitude of the denominator. And that's going to be equal to, so we have a real part here and a real part because this is minus omega squared. And then we have the imaginary part, r1 c1 plus r2 c2. So this is all going to be equal to the square root of 1 minus omega squared r1 c1 r2 c2. So we're going to take that full quantity and square it, and then add it to omega r1 c1 plus r2 c2, and square that entire quantity as well. So now the question asks, for omega close to 0, what is the magnitude of h of j omega? And another easier way to look at this is that if we have the magnitude of h of omega, this is equal to the magnitude of the low pass times the magnitude of the high pass. And this will be equal to, or I could say, if omega is close to 0, so if omega is close to 0, then the magnitude of the low pass, this will be approximately 0. And then the magnitude of the high pass will be approximately 1. And the end result, it'll be approximately 0. As omega goes to infinity, again, we use the logic that it's the magnitude of the low pass times the magnitude of the high pass. And again, we know that the magnitude of the low pass is approximately 0. The magnitude of the high pass is approximately 1. Sorry, for the previous part, I meant to say the magnitude here is 1 and 0. And we can say that the end result is that is approximately 0. So now we'll be taking a look at the cutoff frequency of this filter. We already know that h of omega is equal to, or the magnitude of h of omega is equal to magnitude of the low pass times the magnitude of the high pass. So the idea when we're designing these filters now is we want to make, so with the behavior of the low pass, remember that this was equal to 1 over 1 plus j omega r1 c1. And the shape of the low pass, or the shape of the graph, kind of looked like this, where it was high and then it dropped off. And in the behavior of the high pass was that it was 1 over, or sorry, not 1 over, it was j omega r2 c2 all over 1 plus j omega r2 c2, and the graph looked something like this. So now we want to pick the cutoffs where the low pass is a higher cutoff and the high pass is a lower cutoff. And what this means is we want this such that the low pass is close to 1 when the high pass is 1 over square root of 2. Or we want the low pass to be 1 over square root of 2 when the high pass is close to 1. So with this logic, we'll have two cutoff frequencies. So cutoff 1 is going to be equal to, and these are all approximations, but they'll be equal to 1 over r1c1, and the second one will be 1 over r2c2. Another way of finding these cutoff frequencies was to take the magnitude in the previous part over here, this entire expression, and then set that equal to 1 over the square root of 2 and solve. And the cutoff frequencies would have been slightly different, but they would be approximately 1 over r1c1 and 1 over r2c2. So now if we were to plot these cutoff frequencies, if we know that r1c1 is equal to 100, meaning it's going to be around 1 over square root of 2 at 100, and then r2c2 is equal to 1, we know it's 0 near 0 and 0 near infinity. So if we start sketching, it'll look something like this. So now we'll be taking a look at a second example of a bandpass filter. This has a slightly different design. So we have one inductor, one capacitor, and then we're taking the output between a resistor. So if we want to find the transfer function of this bandpass filter, this will be equal to ZR all over ZR plus ZL plus ZC, which will then be equal to R all over R plus j omega L plus 1 over j omega C. And alternatively, this can be written as, so because we know 1 over j omega C is equal to minus j over omega C, we can write this as R all over R plus j omega L, or j times omega L minus 1 over omega C. Now if we want the magnitude of this transfer function, remember the magnitude is the magnitude of the numerator, which is just R, all over the magnitude of the denominator, which will then be R squared plus omega L minus 1 over omega C squared. Now for omega close to 0, what is the magnitude of h of omega? So the magnitude of h of omega, so if omega is very close to 0, this means omega L will be really small and 1 over omega C will be really big. Which means we can rewrite this, so it's approximately equal to R all over the square root of R squared plus minus 1 over omega C squared. And as omega is very close to 0, we see that this number is very large, and if the denominator is really large while the numerator is constant, this will go to 0. Similarly, for omega going to infinity, if we take a look at the original transfer function, omega L will be really large, whereas 1 over omega C will go to 0. So this is approximately equal to R all over the square root of R squared plus the omega L squared. And as omega is really, really large, this term omega L will be really, really large, meaning the denominator is really large, so this will go to 0 as well. We are now going to compute the cutoff frequencies of this filter. Remember that the cutoff frequency omega C is defined to be as the max, or is defined to be omega C such that the magnitude of the transfer function is equal to the max magnitude all over the square root of 2. So the first thing we need to do is to compute the max magnitude. And the max magnitude will actually be when omega L minus 1 over omega C is equal to 0. So max when omega L minus 1 over omega C is equal to 0. And this is when omega is equal to 1 over the square root of LC. So we know the max is in fact equal to, when this is 0, it's r over the square root of r squared, so the max is 1. So we want to find when the cutoff, or when the magnitude is equal to 1 over the square root of 2. And now we have a bunch of square roots, so to make our calculations easier, I'm just going to take a look at h of omega squared, which is then equal to r all over r squared plus omega L minus 1 over omega C squared is equal to 1/2 squared on the top. Then if we multiply both sides, we'll see that 2r squared is equal to r squared plus omega L minus 1 over omega C squared, meaning r squared is equal to omega L minus 1 over omega C squared. If I square root both sides, I'll get r is equal to plus or minus omega L minus 1 over omega C. And now if I write this as a quadratic equation, I will get something of the form, so multiplying everything by omega C, I'll get omega RC is equal to plus or minus omega squared LC minus 1, which means my equations will be omega squared LC minus 1 minus omega RC is equal to 0, and omega squared LC minus 1 plus omega RC is equal to 0. Now here, I'll technically have 4 answers, but I'm only going to consider the positive ones, which means I'll get omega squared minus omega r over L minus 1 over LC is equal to 0, omega squared minus omega r over L, or plus omega r over L minus 1 over LC is equal to 0, which means by the quadratic formula I'll have omega is equal to r over 2L plus or minus the square root of 1/2 times r over L squared plus 4 over LC. And I'll also get r over 2L plus or minus, it'll be minus r over 2L plus or minus 1/2 square root of r over L squared plus 4 over LC. And it happens that the positive ones will be omega C1 is equal to r over 2L plus 1/2 square root of r over L squared plus 4 over LC. And then the other cutoff frequency is going to be, it's going to be minus r over 2L plus 1/2 square root of r over L squared plus 4 over LC. Now let's pick some values to plot. So let's just say that, so we know the maximum is at omega equals 1 over LC, 1 over square root of LC. So let's say 1 over square root of LC is equal to 10. And then the difference between our cutoffs, omega C1 minus omega C2, is equal to r over L. And I'm going to say that's approximately equal to like 3. So then I know the maximum is over here at 10. Let's say this is around like 3 away, and we know it's near 0 at the ends. So the actual graph will look something along the lines of this. Maybe I drew it a little too far apart, but you should get the gist, where this will be, I'm just going to draw a line over here. This will be omega C1, and then this over here will be omega C2. the last topic we're going to be talking about are the differences between the two bandpass filters we discussed. The differences between the RC/CR with an op-amp bandpass filter and the LRC bandpass filter. So the two filters have very similar behavior at 0 and infinity, as you can see on the graphs over here, but have different bandwidths. So we're going to define bandwidth as the high cutoff frequency minus the low cutoff frequency. So if we look at the graphs over here, we see that the high cutoff frequency is over here and the low cutoff frequency is over here. Similarly for the RLC bandpass, the high cutoff is here and the low cutoff is here. And when it comes to designing these filters, the real trade-off is in the bandwidth, in that the RC/CR has a very large, let's say 1 to 100, so a bandwidth of 99, whereas the filter over here, I think we said that like the bandwidth was 3 or something, where we said that like delta omega C1 minus delta omega C2 was equal to 3. And it depends on what we want from our filter as well. If we want our filter to capture a very wide range of frequencies, then we want a RC/CR bandpass. Whereas if we have a very narrow range of frequencies we want to capture, then we're going to use an RLC bandpass.